By the final decades of the 19th century, physics stood at what many believed was a triumphant endpoint. The laws governing motion, energy, heat, electricity, magnetism, and light appeared complete, elegant, and universally valid. Newton's mechanics had explained the movement of planets and falling apples with the same mathematical precision. Maxwell's equations unified electricity, magnetism, and optics into a single framework that described light as an electromagnetic wave. Thermodynamics had formalized the rules of heat and energy, placing firm limits on what machines could and could not do. To many physicists, nature seemed essentially solved. The universe appeared to be a vast, predictable mechanism, governed by continuous laws that, in principle, allowed every future event to be calculated if the present state were known. This confidence was not casual optimism, but the product of genuine success. Classical physics had delivered results of astonishing accuracy. Astronomers could predict eclipses decades in advance. Engineers built bridges, steam engines, and electrical systems using physical laws that worked reliably every time. Spectroscopy revealed the fingerprints of elements in distant stars, confirming that the same physics applied across the cosmos. Even the behavior of gases, once mysterious, could be explained statistically through the motion of countless atoms obeying Newton's laws. In lecture halls and textbooks, physics was presented as a nearly finished structure, awaiting only refinement. Yet beneath this surface of certainty, cracks were beginning to appear. Certain experimental results stubbornly resisted explanation, no matter how skillfully classical theories were applied. These anomalies were not immediately seen as signs of a coming revolution. Instead, they were viewed as technical problems, small puzzles that clever mathematics or more precise measurements would eventually resolve. History would show, however, that these unresolved issues were not minor imperfections, but fundamental contradictions that pointed to deep flaws in the classical worldview. One source of tension lay in the nature of radiation. Classical physics treated energy as a continuous quantity, capable of varying smoothly without restriction. Light, understood through Maxwell's theory, was a wave phenomenon spreading through space in an unbroken manner. This wave picture worked extraordinarily well for explaining reflection, refraction, interference, and diffraction. However, when physicists attempted to apply these same ideas to the emission and absorption of radiation by matter, serious problems emerged. Experiments involving heated objects, glowing filaments, and thermal radiation produced results that could not be reconciled with classical assumptions. The conflict was especially evident in studies of thermal radiation. When an object is heated, it emits electromagnetic radiation with a characteristic spectrum that depends only on its temperature. Physicists measured this spectrum with increasing precision and found a smooth distribution of energy across different wavelengths. Classical theories attempted to derive this distribution using established principles of mechanics, electromagnetism, and thermodynamics. The results were disastrous. Calculations predicted that as the wavelength of radiation decreased, the emitted energy should increase without bound, leading to an infinite total energy output. This prediction was not just inaccurate, but physically impossible. This failure was deeply troubling because it struck at the heart of classical reasoning. The equations leading to the incorrect result were not sloppy or experimental approximations. They followed logically from well-established laws. If these laws produced nonsense when applied to real systems, then something fundamental was wrong. Yet at the time, few were ready to question the foundations themselves. Instead, physicists searched for corrections, adjustments, or hidden assumptions that might restore consistency without abandoning continuity and determinism. Another challenge to classical physics emerged from the study of atomic structure. Atoms were increasingly accepted as real physical entities rather than mere theoretical conveniences. Chemical behavior, gas laws, and spectral lines all pointed toward a discrete atomic picture of matter. However, classical mechanics and electromagnetism could not explain how atoms remained stable. According to classical theory, electrons orbiting a nucleus should continuously radiate energy and spiral inward, causing atoms to collapse in a fraction of a second. Matter, as it clearly existed, should not be stable at all. Spectroscopy added to this puzzle. When atoms emitted or absorbed light, they did so at sharply defined frequencies, producing discrete spectral lines rather than continuous bands. Classical physics offered no natural explanation for this selectivity. If electrons behaved like tiny orbiting charges, they should emit radiation over a wide range of frequencies. The observed regularity and precision of spectral lines suggested an underlying order that classical ideas could not capture. The problem extended beyond atoms and radiation into thermodynamics and statistical mechanics. The equipartition theorem, a cornerstone of classical statistical physics, predicted that energy should be evenly distributed among all available degrees of freedom. Applied to real systems, this theorem led again to infinities and contradictions. Certain modes of motion appeared to carry no energy at all, contrary to classical expectations. Attempts to reconcile theory with experiment required ad hoc assumptions that weakened confidence in the overall framework. Despite these difficulties, the dominant attitude among physicists remained conservative. The prevailing belief was that classical physics was fundamentally correct, and that its apparent failures were due to incomplete understanding or experimental limitations. Some prominent figures even warned against radical speculation, urging younger scientists to focus on precision measurements rather than conceptual upheaval. Ironically, this very confidence delayed recognition of the depth of the crisis. At the same time, the philosophical implications of classical physics reinforced resistance to change. Classical laws implied a deterministic universe, one in which the future was fully determined by the past. This vision aligned with broader intellectual currents emphasizing order, predictability, and rational control. To question the continuity of energy or the universality of classical laws seemed to threaten not just physics, but a world view that had shaped scientific thinking for centuries. Yet experiments continued to accumulate, and the discrepancies refused to disappear. Improved instruments only sharpened the conflict between theory and observation. The more accurately physicists measured radiation spectra, atomic behavior, and thermal properties, the clearer it became that classical explanations were inadequate. What had once appeared as small cracks began to resemble structural faults. This growing tension marked the true crisis of classical physics. It was not a sudden collapse, but a slow realization that the existing framework could not account for all aspects of nature. The crisis was intellectual rather than practical. Classical physics still worked superbly for everyday phenomena and engineering applications. But at microscopic scales and extreme conditions, its authority was breaking down. The importance of this crisis lay not only in the problems themselves, but in what they demanded of scientists. Solving these puzzles would require abandoning deeply held assumptions about continuity, determinism, and the nature of physical reality. It would require accepting that classical concepts, so successful at human scales, might fail at the smallest levels of nature. This realization set the stage for one of the most profound transformations in scientific history. The end of the 19th century thus represents a turning point. Physics stood between two worlds, one defined by the smooth, predictable laws of classical thought, and another, not yet fully imagined, in which energy, matter, and information behaved in fundamentally new ways. The crisis of classical physics was not a sign of failure, but a sign of growth. It revealed the limits of old ideas and created the conditions necessary for a revolutionary breakthrough. From this intellectual tension, a new understanding of nature would soon emerge, reshaping physics and redefining humanity's picture of the universe. As the 19th century drew to a close, one of the most troubling puzzles in physics centered on a deceptively simple question: how does matter emit light when it is heated? At first glance, the phenomenon seemed ordinary. A piece of iron glows red when heated, then orange, then white as its temperature rises. This behavior was familiar to blacksmiths and engineers long before physicists studied it in laboratories. Yet when scientists attempted to explain this everyday observation using the laws of classical physics, they encountered a problem so severe that it threatened the logical consistency of the entire theoretical framework. To study thermal radiation in a controlled way, physicists introduced the concept of a blackbody. A blackbody was not necessarily black in color, but was defined as an idealized object that absorbs all radiation that falls upon it, and emits radiation in a way that depends only on its temperature, not on its material composition or shape. In practice, a small hole in the wall of a heated cavity behaved almost exactly like a blackbody. Radiation entering the hole would bounce around inside, being absorbed and re-emitted until it reached thermal equilibrium. The radiation escaping from the hole provided a pure example of thermal radiation, free from the complexities of real materials. Careful experiments revealed a remarkable regularity in blackbody radiation. At any given temperature, the emitted radiation followed a smooth, well-defined distribution across different wavelengths. As the temperature increased, the total energy emitted rose, and the peak of the spectrum shifted toward shorter wavelengths. These patterns were measured with increasing precision throughout the late 19th century, producing curves that experimentalists could reproduce reliably in laboratories across Europe. The challenge was not the data, but the theory. Classical physics approached this problem using established principles. Electromagnetic radiation was treated as waves, and the energy of these waves was assumed to vary continuously. Inside the blackbody cavity, radiation was modeled as standing electromagnetic waves bouncing between the walls. According to classical statistical mechanics, each possible mode of vibration should carry an average amount of energy determined by the temperature. This reasoning was elegant and seemingly unavoidable, as it followed directly from the equipartition theorem, one of the cornerstones of classical thermodynamics. When physicists applied this logic, the results were initially promising at long wavelengths. The theoretical predictions matched experimental data reasonably well in the infrared region of the spectrum. However, as calculations extended to shorter wavelengths, the theory began to diverge dramatically from reality. The equations predicted that the energy density of radiation should increase without limit as the wavelength decreased. In other words, a blackbody should emit enormous amounts of energy at ultraviolet and higher frequencies. This prediction was not merely inaccurate, it was absurd. If it were true, any warm object would radiate infinite energy, instantly cooling to absolute zero. The fact that the world clearly did not behave this way exposed a catastrophic failure of classical theory. This discrepancy became known as the Ultraviolet Catastrophe, a name that captured both the mathematical divergence and the sense of crisis it provoked among physicists. What made the problem especially disturbing was that it arose from principles that were otherwise extraordinarily successful. The equipartition theorem had explained the behavior of gases with great accuracy. Maxwell's electromagnetic theory had unified light, electricity, and magnetism in a single mathematical framework. There was no obvious mistake in the logic or mathematics. The catastrophe seemed to imply that classical physics, when applied consistently, led to conclusions that contradicted physical reality. Physicists responded to this dilemma in various ways. Some attempted to modify the theoretical assumptions, introducing arbitrary cutoffs or constraints that limited the number of allowed radiation modes. Others searched for subtle errors in the derivations, hoping to find a missing factor that would tame the divergence at short wavelengths. These efforts achieved limited success, but lacked a solid physical justification. The fixes felt artificial, imposed to save the theory rather than arising naturally from its principles. Meanwhile, experimental evidence continued to accumulate. Improved instruments allowed more precise measurements of blackbody spectra across a wide range of temperatures and wavelengths. The experimental curves were smooth, finite, and reproducible, standing in stark contrast to the infinite predictions of classical theory. The more accurate the measurements became, the clearer it was that the failure lay not in the data, but in the theoretical assumptions themselves. The blackbody radiation problem also had broader implications beyond thermal physics. Radiation played a central role in understanding energy transfer, chemical reactions, and the interaction between matter and light. If classical physics could not correctly describe something as fundamental as thermal radiation, its authority over microscopic processes was seriously undermined. This realization began to erode the confidence that physics was nearing completion. At the heart of the problem was the classical assumption of continuity. Energy, according to traditional theory, could be divided into arbitrarily small amounts. There was no minimum unit, no smallest packet. In the context of blackbody radiation, this assumption allowed infinitely many modes of vibration to contribute energy, leading directly to the ultraviolet catastrophe. Yet nature appeared to impose a limit that theory could not explain. Despite the severity of the problem, few physicists initially interpreted it as a sign that energy itself might be quantized. The idea that energy could come in discrete units seemed radical and counterintuitive, contradicting centuries of physical intuition. Waves, by their very nature, were continuous, and light had been firmly established as a wave phenomenon. To suggest otherwise felt like a step backward. Instead, the blackbody problem was treated as an isolated anomaly, a technical challenge to be solved within the existing framework. This attitude delayed recognition of its deeper significance. In hindsight, the ultraviolet catastrophe was not a failure of calculation, but a signal that the foundational assumptions of classical physics were incomplete. The stage was now set for a conceptual breakthrough. The blackbody radiation problem demanded an explanation that could reproduce the observed spectra without resorting to infinities or arbitrary fixes. It required a new way of thinking about how energy is exchanged between matter and radiation. Whoever solved this problem would not only resolve a long-standing puzzle, but would also open the door to a fundamentally new understanding of nature. This unresolved tension placed blackbody radiation at the center of the coming revolution in physics. What began as a study of heated cavities and glowing objects had evolved into a profound challenge to the classical world view. The problem was no longer whether classical physics could be adjusted slightly to fit the data, but whether its core assumptions about energy and continuity were valid at all. From this crisis would emerge an idea so simple yet so radical that it would transform physics forever. At the center of the growing crisis in physics stood Max Planck, a man whose temperament and scientific philosophy made him an unlikely revolutionary. Planck was not a radical thinker seeking to overthrow established ideas. On the contrary, he was deeply committed to the principles of classical physics and believed strongly in the existence of absolute physical laws. For him, nature was governed by precise mathematical relationships that reflected an objective reality independent of human observation. This belief shaped his entire approach to science and made his eventual contribution all the more remarkable. Planck's involvement with the problem of thermal radiation began not from a desire to challenge classical physics, but from a practical and theoretical necessity. Experimental measurements of blackbody radiation were becoming increasingly accurate, and industry, particularly the development of electric lighting, demanded a better understanding of how materials emitted light at different temperatures. Planck saw an opportunity to apply rigorous thermodynamic reasoning to derive a formula that would describe the observed radiation spectrum exactly. At the time, several partial solutions existed. Some formulas matched experimental data at long wavelengths, while others worked reasonably well at short wavelengths. None, however, provided a unified description across the entire spectrum. Planck found this situation unsatisfactory. From his perspective, a true physical law had to be universally valid, not a patchwork of approximations that worked only under limited conditions. Planck approached the problem using the tools he trusted most: thermodynamics and statistical reasoning. He believed that entropy held the key to understanding radiation, just as it had explained many irreversible processes in physics. By focusing on entropy rather than microscopic mechanical details, Planck hoped to bypass the difficulties that plagued classical electrodynamics and arrive at a general solution. His strategy involved modeling the walls of a blackbody cavity as containing countless tiny oscillators, sometimes called resonators. These oscillators were imagined to absorb and emit electromagnetic radiation at specific frequencies. This model was not meant to describe the literal structure of matter, but to provide a mathematical framework for calculating how energy was exchanged between matter and radiation. Within this framework, Planck sought to determine how energy would be distributed among the oscillators when the system reached thermal equilibrium. Initially, Planck assumed that energy could vary continuously, in accordance with classical physics. Using this assumption, he attempted to derive the entropy of the oscillators as a function of their energy and frequency. From this entropy expression, he aimed to calculate the radiation spectrum emitted by the cavity. Despite his mathematical skill, the results stubbornly failed to match experimental observations across all wavelengths. As months turned into years, Planck found himself repeatedly returning to the same obstacle. No matter how he refined his calculations, the classical assumption of continuous energy led either to incorrect spectra or to mathematical inconsistencies. This was deeply frustrating for Planck, who regarded the laws of thermodynamics as almost sacred. The idea that they might need modification was unthinkable to him. Under mounting pressure to explain the data, Planck made a critical shift in perspective. Rather than questioning thermodynamics, he questioned how it was being applied at the microscopic level. This shift did not come easily. It required him to entertain a possibility that contradicted his physical intuition. that energy exchange might not be continuous after all. In a move he later described as an act of desperation, Planck introduced a new assumption into his calculations. He proposed that the energy of each oscillator could take on only certain discrete values rather than varying smoothly. Specifically, the energy would be restricted to integer multiples of a basic unit proportional to the oscillator's frequency. This assumption was not derived from experimental evidence or physical reasoning, but was introduced purely to make the mathematics work. With this single change, the problem transformed. Planck was able to calculate the entropy of the oscillators in a way that produced a radiation formula matching experimental results perfectly across all wavelengths. The infinities vanished. The ultraviolet catastrophe was avoided. For the first time, there was a single equation that described Blackbody radiation accurately at all temperatures. Despite this success, Planck did not immediately interpret his assumption as a statement about physical reality. To him, it was a mathematical device, a convenient trick to obtain the correct result. He believed that a deeper classical explanation would eventually emerge, one that would justify the discrete energy values without abandoning continuity at a fundamental level. Nevertheless, the introduction of discrete energy elements had profound implications. It meant that energy exchange between matter and radiation occurred in finite steps, not as a smooth flow. This idea clashed directly with classical wave theory and raised uncomfortable questions about the nature of light and matter. Planck formalized his assumption by introducing a new constant of nature, a proportionality factor linking energy and frequency. This constant was extraordinarily small, reflecting why the effects of energy quantization had gone unnoticed in everyday phenomena. At ordinary scales, energy appeared continuous because the discrete units were too tiny to detect. The constant soon became known as Planck's constant, and it represented the smallest possible action in physical processes. Although Planck himself did not yet grasp its full significance, he understood that he had uncovered something fundamental. The constant was not an adjustable parameter, but a fixed number determined by nature itself. The reaction to Planck's work was cautious and, in some cases, skeptical. Many physicists admired the elegance of his formula, but were uneasy about its underlying assumption. The idea that energy was quantized seemed artificial and lacked a clear physical interpretation. Some hoped that future work would eliminate the need for such an assumption altogether. Planck shared this hope. He continued to search for a classical explanation that would restore continuity while preserving the success of his radiation law. Yet as time passed, no such explanation emerged. Instead, other physicists began to explore the consequences of Planck's idea more boldly. What made Planck's struggle so significant was not just the result he obtained, but the way it revealed the limits of classical reasoning. A problem that resisted solution for decades was resolved only by stepping outside the accepted framework. This did not mean that classical physics was wrong in all cases, but it was no longer sufficient to describe nature at its most fundamental level. Planck's personal reluctance to embrace the revolutionary implications of his work highlights the depth of the conceptual shift involved. The transition from continuous to discrete thinking was not merely a technical adjustment, but a transformation in how physicists understood reality. Energy, once seen as infinitely divisible, now appeared to be built from indivisible units. By the time Planck published his results, the groundwork for a new physics had been laid, even if its full structure was not yet visible. His struggle to explain energy distribution marked a turning point, demonstrating that empirical truth could force even the most conservative thinkers to adopt radical ideas. The quiet persistence of experimental data had prevailed over tradition. This moment did not yet constitute a complete revolution, but it set one in motion. Planck's solution to the Blackbody problem opened a door that others would soon push wider. His reluctant step away from classical continuity would become the first stride into the quantum world, reshaping physics in ways he could scarcely have imagined. The idea that energy might come in discrete packets marked a profound departure from everything physics had assumed for centuries. Before this moment, continuity was not merely a useful approximation, but a deeply embedded principle. Motion was continuous, forces acted smoothly, and energy flowed without interruption. Waves, in particular, embodied continuity. Whether ripples on water or oscillations of light, waves were understood as extended disturbances that could be divided endlessly without losing their essential character. Against this background, the suggestion that energy exchange occurred in indivisible steps appeared almost unthinkable. Yet the mathematical success of Planck's radiation formula forced physicists to confront this unsettling possibility. The assumption that energy could only be absorbed or emitted in fixed amounts was not introduced because it seemed philosophically appealing, but because nothing else worked. The experimental evidence demanded it. The smooth curves measured in Blackbody radiation experiments emerged naturally only when energy was restricted to discrete values. Continuity, once the foundation of explanation, had become an obstacle. What made the idea especially radical was that it challenged the wave theory of light at its core. If light was a wave, how could its energy be transferred in chunks rather than continuously? In classical wave theory, the energy of a wave depended on its amplitude, which could vary smoothly. There was no natural mechanism for enforcing minimum units. Planck's proposal seemed to graft a discrete rule onto an otherwise continuous theory, creating a tension that few knew how to resolve. At first, many physicists treated the idea of energy packets as a purely formal assumption. It was seen as a bookkeeping device, a mathematical constraint imposed on oscillators in the walls of a cavity rather than a statement about the nature of light itself. This interpretation allowed scientists to preserve their belief in continuity while still using Planck's formula. The deeper implications were acknowledged but postponed. Despite this caution, the language of discrete energy elements began to spread. The term quantum, derived from the Latin word for how much, came to represent the smallest amount of energy that could be exchanged at a given frequency. This was not a particle in the traditional sense, but it was not a classical wave either. It occupied an uncomfortable middle ground, defying easy classification. The radical nature of this idea became clearer as physicists explored its consequences. If energy exchange was quantized, then microscopic processes could not be described as smooth, continuous evolutions. Instead, systems would change in jumps, moving abruptly from one allowed state to another. This ran counter to classical intuition, which pictured nature as evolving through infinitesimal steps. The resistance to this notion was not merely technical, but deeply conceptual. Classical physics had shaped how scientists thought about causality and predictability. Continuous change allowed equations of motion to be written as smooth functions of time, making the future behavior of systems calculable in principle. Discrete jumps, by contrast, suggested a world in which change occurred in sudden transitions that classical equations could not easily describe. The idea of quantized energy also raised questions about measurement and observation. If energy could only be exchanged in fixed units, what happened to smaller amounts? Were they forbidden entirely, or simply unobservable? These questions hinted at a limit to how finely nature could be probed, a notion that would later become central to quantum theory. Initially, Planck himself avoided confronting these issues. He continued to view quantization as a feature of matter's interaction with radiation, not of radiation itself. In his mind, the oscillators in the cavity walls were constrained by unknown mechanisms that forced them to emit and absorb energy in discrete amounts. Light, once emitted, could still behave as a continuous wave. This compromise allowed Planck to remain within the conceptual boundaries of classical physics, at least temporarily. However, the simplicity of the quantization rule made it difficult to dismiss as a mere artifact. A single proportionality between energy and frequency, governed by a universal constant, explained an entire class of phenomena with remarkable accuracy. The elegance of this result suggested that it reflected something real about nature rather than an artificial constraint. As discussions spread through the physics community, reactions varied widely. Some physicists admired the empirical success of the idea while remaining skeptical of its interpretation. Others sensed that a fundamental shift was underway. Younger scientists, less invested in classical tradition, were often more willing to explore the implications of quantization openly. The radical idea of energy packets also began to intersect with other unresolved problems. Spectral lines, which had long resisted classical explanation, now appeared in a new light. If atoms could exchange energy only in discrete amounts, then the sharp frequencies observed in emission and absorption spectra might reflect transitions between quantized energy states. This possibility suggested a unifying principle underlying diverse phenomena. The notion of quantization also implied that nature contained built-in limits. Just as matter was composed of atoms, energy might be composed of indivisible units. This analogy was powerful. The acceptance of atoms had once faced strong resistance, yet atoms were now essential to understanding chemistry and thermodynamics. Perhaps energy quanta represented a similar conceptual leap. Still, the discomfort remained. Waves and particles had long been treated as distinct categories, each governed by different laws. Quantized energy blurred this distinction. It suggested that light, the quintessential wave, might exhibit particle-like properties under certain conditions. This idea threatened the clarity of classical classifications and foreshadowed a more complex picture of physical reality. The radical nature of quantization lay not only in its discreteness, but in its universality. Planck's constant appeared to be the same for all systems, regardless of their composition or scale. This universality implied that quantization was not a special feature of certain materials, but a fundamental aspect of the interaction between energy and matter. As the implications of this idea slowly unfolded, it became clear that accepting energy quanta would require rethinking some of the most basic assumptions of physics. Continuity, determinism, and the clear separation between waves and particles could no longer be taken for granted. The classical picture of a smooth, predictable universe was giving way to a more granular and subtle reality. At this stage, however, the revolution was still incomplete. The idea of discrete energy packets had been introduced, but its meaning was not yet fully understood. It existed as a powerful but unsettling concept, capable of explaining stubborn experimental facts while raising profound questions about the nature of light and matter. This tension defined the moment. Physics stood at the threshold of a new way of thinking, driven not by philosophical speculation, but by the quiet insistence of empirical evidence. The radical idea of energy quanta had entered the scientific imagination, and once introduced, it could not be ignored. It would soon be taken up, extended, and transformed by others, leading to consequences far beyond its original context. The acceptance of discrete energy packets marked the point at which classical continuity began to fracture. What followed would be an exploration of this fracture, revealing a world in which nature operates according to rules that defy everyday intuition, yet describe reality with unprecedented precision. The step from continuous flow to quantized exchange was small in mathematical form, but immense in conceptual impact, setting the stage for the full emergence of quantum physics. The introduction of a new constant into physics is never a trivial event. Physical constants represent more than numerical values. They encode deep truths about how nature operates. When Max Planck introduced what would later be called Planck's constant, he was not merely adjusting an equation to fit data. He was identifying a new boundary in the description of physical reality, a boundary that marked the limit of classical concepts and hinted at a deeper structure beneath them. Planck's constant emerged naturally from his attempt to describe Blackbody radiation accurately. In his revised formula, energy was directly proportional to the frequency of radiation, with the proportionality factor given by a new constant. This constant was extraordinarily small, so small that its effects were imperceptible in everyday phenomena. At first glance, it seemed like an abstract numerical artifact, introduced solely to make the mathematics agree with experiment. Yet its smallness was precisely what made it significant. Because the constant was tiny, classical physics appeared to work almost perfectly at macroscopic scales. The discrete nature of energy exchange was hidden beneath the smooth behavior observed in daily life. Only at microscopic scales, or under extreme conditions, did the effects of this constant become unavoidable. In this way, Planck's constant explained both the success of classical physics and its ultimate failure. Planck interpreted this constant as defining the smallest possible unit of action in nature. Action, in classical mechanics, is a quantity that combines energy and time, or momentum and distance. It plays a central role in the formulation of physical laws, particularly in variational principles that determine the paths systems follow. By introducing a smallest action, Planck was effectively stating that nature does not allow arbitrarily small changes in physical processes at the fundamental level. This idea challenged deeply rooted assumptions. Classical physics assumed that action, like energy, could vary continuously and be divided without limit. There was no smallest step, no fundamental grain. Planck's constant imposed a limit, suggesting that below a certain scale, classical descriptions lose meaning. Processes could no longer be subdivided indefinitely. There was a minimum unit beyond which the concept of smooth change broke down. At first, Planck himself did not fully embrace this interpretation. He regarded the constant as a feature of his radiation law rather than a universal property of nature. Nonetheless, its appearance was striking. Unlike many constants introduced in physics, Planck's constant was not associated with a particular material or system. It was universal, the same for all forms of radiation and all oscillators, regardless of their composition. This universality hinted that the constant was revealing something fundamental. If the same smallest unit of action applied everywhere, then it must reflect a deep property of the natural world rather than an incidental detail. Over time, physicists began to recognize that Planck's constant set the scale at which quantum effects become important, separating the classical domain from the quantum domain. The constant also introduced a new way of thinking about physical limits. Just as the speed of light defines an upper limit for the transmission of information and motion, Planck's constant defines a lower limit for action. Together, these constants constrain what is physically possible, shaping the structure of physical law. They reveal that nature is not infinitely flexible, but governed by fundamental boundaries. As Planck's work circulated, the numerical value of the constant was measured more precisely. Its consistency across different experiments reinforced confidence in its significance. The constant appeared not only in blackbody radiation, but also in phenomena that would soon be recognized as deeply related, such as atomic spectra and photoelectric emission. Each new appearance strengthened the case that Planck's constant was a cornerstone of a new physics. The idea of a smallest action also had philosophical implications. It suggested that the classical notion of determinism might need revision. If physical processes occurred in discrete units, then the smooth trajectories and continuous evolutions described by classical equations were approximations rather than exact descriptions. At very small scales, nature might operate according to rules that did not fit neatly into the deterministic framework. Despite these implications, acceptance was gradual. Many physicists treated Planck's constant as a useful parameter rather than a fundamental principle. They used it to calculate radiation spectra without committing to a new interpretation of reality. This cautious approach reflected the difficulty of abandoning familiar concepts that had served science so well. Nevertheless, the constant quietly reshaped theoretical thinking. Its presence in equations acted as a reminder that classical assumptions had limits. When calculations produced infinities or contradictions, Planck's constant often provided the means to restore finiteness and consistency. In this way, it became a tool for navigating the boundary between classical and quantum descriptions. The recognition of Planck's constant as the smallest action also unified diverse areas of physics. It linked thermodynamics, electromagnetism, and mechanics in a new way, revealing connections that classical theory had obscured. This unification suggested that quantum principles were not confined to exotic phenomena, but were woven into the fabric of physical law. As younger physicists engaged more deeply with these ideas, they began to explore their consequences with greater boldness. The constant was no longer seen as a technical detail, but as a guide to a new theoretical landscape. It hinted at new forms of dynamics, new rules for measurement, and new interpretations of physical quantities. Planck himself remained cautious, but he recognized that his constant had uncovered something enduring. It was not an adjustable parameter to be replaced by future refinements, but a fixed feature of nature. Its value had to be measured, not derived, underscoring its status as a fundamental constant. In time, Planck's constant would come to occupy a central place in quantum theory, appearing in equations that describe atomic structure, wave behavior, and uncertainty relations. Its role as the smallest action would shape the development of physics throughout the 20th century and beyond. At this early stage, however, the full significance of the constant was still unfolding. It stood as a quiet marker of a boundary that classical physics could not cross. By defining a minimum scale for action, Planck's constant revealed that the universe is not infinitely divisible but structured in a subtle, quantized way. The introduction of this constant marked a decisive step toward a new understanding of nature. It transformed a mathematical solution into a physical principle, one that would guide the emerging quantum theory. Though modest in numerical value, Planck's constant carried enormous conceptual weight. signaling the end of an era of unrestricted continuity and the beginning of a physics governed by fundamental limits. The introduction of quantized energy struck at the very heart of classical physics because it challenged assumptions that had guided scientific thought for more than 2 centuries. Classical physics was built on continuity, determinism, and clear causal relationships. Every physical quantity was assumed to change smoothly, and every effect was thought to follow precisely from a prior cause. Planck's idea disrupted this orderly picture in subtle but profound ways, revealing cracks in the foundations that could no longer be ignored. In classical mechanics, motion is described through continuous trajectories. A particle moves from one position to another by passing through every intermediate point. Its energy can be adjusted by arbitrarily small amounts, and its future behavior can be predicted exactly if its present state is known. This framework had proven extraordinarily successful, from predicting planetary orbits to explaining the motion of projectiles. The assumption of continuity was not merely convenient. It was essential to how classical equations were formulated. Electromagnetic theory reinforced this worldview. Maxwell's equations described electric and magnetic fields as smooth, continuous functions spread throughout space. Light, as an electromagnetic wave, was understood as a continuous oscillation that could vary in intensity without restriction. The energy carried by light waves depended on their amplitude, which classical theory allowed to take any value. There was no place in this picture for minimum units or discrete jumps. Planck's proposal directly contradicted this assumption. By asserting that energy could only be exchanged in fixed amounts, he implied that systems could not change continuously at the most fundamental level. Instead of a smooth flow of energy, there were sudden transitions. This idea conflicted with the mathematical structure of classical theories, which relied on differential equations describing infinitesimal changes. If changes occurred in finite steps, the classical machinery lost its validity. The contradiction became especially clear in the context of radiation. Classical wave theory predicted that energy could be distributed among infinitely many wave modes, each carrying a small amount of energy. This led naturally to the ultraviolet catastrophe. Planck's quantization rule imposed a restriction that classical theory did not permit, effectively cutting off the contribution of high-frequency modes. From a classical perspective, this restriction appeared arbitrary and unjustified. Another point of conflict lay in the relationship between energy and frequency. Classical physics treated these as independent quantities. The frequency of a wave was determined by its source, while its energy depended on its amplitude. Planck's formula linked energy directly to frequency, suggesting a deeper connection that classical theory did not anticipate. This linkage implied that changing the frequency of radiation altered the fundamental unit of energy exchange, a concept foreign to classical thinking. The idea of quantization also undermined classical statistical mechanics. The equipartition theorem, which assigned equal average energy to each degree of freedom, depended critically on the assumption that energy could vary continuously. Planck's constant invalidated this assumption at small scales, explaining why equipartition failed for radiation and certain molecular motions. In doing so, it exposed the limited range of applicability of classical statistics. Classical physics also assumed that measurements could, in principle, be made with unlimited precision. If quantities were continuous, one could imagine refining measurements indefinitely. Quantization introduced a natural granularity that challenged this ideal. If energy exchanges occurred in discrete units, then below a certain scale, the notion of measuring smaller differences lost meaning. This hinted at fundamental limits to knowledge that classical physics had never considered. The contradiction extended to the concept of causality. In classical theory, change is gradual and predictable. Quantized transitions, by contrast, suggested abrupt changes that could not be described as the cumulative result of infinitesimal causes. While Planck himself did not emphasize this implication, it lay dormant within the idea, waiting to be developed by later theorists. Resistance to Planck's idea was therefore intense but understandable. Accepting quantization meant questioning not just a particular theory, but the entire conceptual framework of classical physics. It required physicists to accept that their most trusted tools might fail at fundamental scales. For many, this was a step too far, at least initially. Some physicists attempted to reinterpret quantization in ways that preserved classical continuity. They suggested that discreteness arose from unknown properties of matter rather than from energy itself. Others hoped that a deeper classical mechanism would eventually explain why energy appeared quantized without abandoning continuity. These interpretations reflected a desire to retain the familiar structure of classical thought, yet the contradictions persisted. As quantization proved increasingly successful in explaining experimental results, the classical alternatives grew more strained. Each attempt to reconcile Planck's idea with classical assumptions required additional hypotheses that lacked independent justification. The simplicity and effectiveness of quantization stood in contrast to the complexity of classical fixes. The conflict between Planck's idea and classical physics was not a simple disagreement over details, but a clash between worldviews. Classical physics envisioned a universe that was smooth, continuous, and fully intelligible through deterministic laws. Quantization suggested a universe that was granular at its core, governed by limits and discontinuities that defied everyday intuition. This contradiction forced physicists to confront the possibility that classical concepts were approximations rather than fundamental truths. They worked well in regimes where Planck's constant was negligible, but they broke down when that constant could not be ignored. The success of classical physics was thus reinterpreted not as evidence of its ultimate validity, but as a consequence of the smallness of Planck's constant. As this realization slowly spread, it reshaped the way physicists thought about theory and experiment. Instead of assuming that established concepts must apply universally, scientists became more open to the idea that different scales of nature required different descriptions. This shift marked a turning point in the philosophy of physics. At this stage, the contradiction remained unresolved rather than eliminated. Quantization had demonstrated its power, but a coherent alternative framework had not yet emerged. Classical physics still dominated most applications, while quantum ideas hovered at the margins, unsettling but indispensable. The tension between these two views created a fertile ground for further development. It encouraged new experiments, new interpretations, and new mathematical tools. The recognition that Planck's idea contradicted classical physics was not a sign of failure but a catalyst for progress. This contradiction would soon deepen as other phenomena, such as the photoelectric effect in atomic spectra, were examined through the lens of quantization. Each success of the new idea made the limitations of classical physics more apparent. The orderly, continuous universe of classical thought was giving way to a more complex reality, one in which discreteness played a central role. The struggle to reconcile these opposing views defined the early years of quantum theory. Planck's constant stood as a quiet but persistent challenge to classical assumptions, reminding physicists that even the most successful theories have limits. By exposing these limits, Planck's idea opened the path toward a deeper understanding of nature, one that would ultimately replace continuity with quantization at the foundation of physical law. When Max Planck introduced the idea of quantized energy, he did not intend to create a new branch of physics. His goal was modest and precise: to solve a stubborn problem in thermal radiation while preserving the integrity of classical theory. Yet history often advances through unintended consequences, and Planck's work became a clear example of how a cautious solution can trigger a revolutionary transformation. The birth of quantum physics was not announced with fanfare or radical declarations. It emerged quietly from equations written to explain experimental data. At the moment of its introduction, quantization did not look like the foundation of a new world view. It appeared as a technical assumption, useful but limited in scope. Many physicists believed it would eventually be absorbed into classical physics, or replaced by a deeper explanation that restored continuity. This expectation shaped the early reception of Planck's work. His radiation law was praised for its accuracy, while the underlying assumption was often treated as provisional. Despite this cautious attitude, the idea could not remain confined to its original context. The success of Planck's formula encouraged others to apply the same reasoning to different phenomena. Each application extended the reach of quantization and revealed its explanatory power. Slowly, a pattern began to emerge. Problems that had resisted classical explanation for years seemed to yield when discrete energy exchanges were assumed. One of the first signs that something deeper was unfolding came from the study of light itself. Classical theory described light as a wave, and this description had been confirmed by countless experiments. Yet certain observations involving light interacting with matter did not fit comfortably within the wave picture. These anomalies had been noted, but not fully understood. Planck's idea offered a new way to think about them. As physicists explored these connections, it became increasingly difficult to view quantization as a mere mathematical trick. Its ability to resolve diverse problems suggested that it reflected a genuine feature of nature. The constant that Planck had introduced began to appear in new contexts, linking phenomena that had previously seemed unrelated. This growing web of connections hinted at an underlying unity. The unintended nature of this development is crucial to understanding the birth of quantum physics. Unlike earlier revolutions, such as the shift from Newtonian mechanics to relativity, there was no single manifesto or decisive experiment announcing a new theory. Instead, quantum ideas accumulated gradually, driven by necessity rather than ideology. Each step was motivated by the desire to explain data, not to overturn tradition. This gradual emergence created a period of conceptual ambiguity. Physicists found themselves using quantization in calculations while remaining uncertain about its meaning. Was energy truly discrete, or was discreteness a feature of matter's interaction with radiation? Could classical concepts be modified slightly to accommodate these results, or was a more radical departure required? These questions had no immediate answers. The ambiguity allowed quantum ideas to spread without provoking outright rejection. Because quantization solved real problems, it was tolerated even by those who disliked its implications. Over time, this tolerance evolved into acceptance, not through philosophical argument, but through repeated success. Each new application reinforced the idea's legitimacy. The unintended birth of quantum physics also reflected a shift in scientific methodology. Classical physics had relied heavily on visualizable models and mechanical analogies. Quantum ideas resisted such representation. They were abstract, mathematical, and often counterintuitive. Accepting them required physicists to trust equations more than intuition, a significant change in scientific culture. As quantum ideas spread, they began to influence how physicists thought about explanation itself. Instead of demanding a clear mechanical picture, scientists became more willing to accept probabilistic and abstract descriptions. This shift did not happen overnight, but it marked a departure from classical expectations about what a physical theory should provide. Another sign of a new physics was the growing recognition that Planck's constant set a fundamental scale. Phenomena that depended on this constant could not be explained by classical theories alone. This realization unified diverse observations under a single principle, strengthening the case for a new theoretical framework. The unintended nature of the quantum revolution also meant that it developed unevenly. Some areas of physics adopted quantum ideas quickly, while others remained largely classical for decades. This coexistence created tensions, but also opportunities for cross-fertilization. Classical methods continued to be useful, even as their limitations became clearer. As more physicists engaged with these ideas, the language of physics began to change. Terms like quantum, discrete states, and energy levels entered common usage. These concepts were initially vague, but they provided a vocabulary for discussing phenomena that classical language could not adequately describe. The growing influence of quantization also altered the relationship between theory and experiment. Experiments were no longer seen merely as tests of existing theories, but as guides to new principles. Unexpected results were not dismissed as errors, but treated as clues to deeper laws. This openness to surprise became a hallmark of quantum research. The unintended birth of quantum physics highlights the role of humility in science. Planck did not set out to revolutionize physics, and he did not immediately recognize the full significance of his work. His willingness to follow the mathematics where it led, even when it conflicted with his intuition, allowed a new theory to emerge. This episode also illustrates how scientific revolutions can arise from within established traditions rather than from outright rebellion. Quantum physics was born from classical physics, using its tools and concepts, even as it revealed their limits. The continuity between old and new made the transition both more subtle and more profound. By the early years of the 20th century, it was becoming clear that something fundamentally new was taking shape. The accumulation of successful quantum explanations could no longer be dismissed as coincidence. A new framework was needed to organize these ideas and clarify their implications. At this stage, quantum physics existed more as a collection of insights than as a coherent theory. Its principles were powerful but incomplete, its interpretations uncertain. Yet its trajectory was unmistakable. The unintended consequences of Planck's solution had set physics on a new path. The birth of quantum physics was thus not a single moment but a process. It unfolded through a series of small, reluctant steps, each justified by empirical success. This gradual emergence gave the new theory a resilience that dramatic proclamations might not have achieved. What began as a narrow solution to a technical problem had grown into a challenge to the classical world. Without intending to do so, Planck had opened a door that could not be closed. The physics that emerged on the other side would redefine humanity's understanding of nature at its most fundamental level, revealing a world governed not by smooth continuity, but by discrete, quantized processes that defy everyday intuition. The emergence of quantization did not immediately unite the scientific community in agreement or excitement. Instead, it produced a complex mixture of curiosity, skepticism, resistance, and cautious acceptance. Physics at the turn of the 20th century was a mature discipline with deeply established methods, authorities, and traditions. Any idea that threatened its conceptual foundations was bound to face scrutiny, and Planck's proposal was no exception. Many physicists initially focused on the practical success of Planck's radiation formula, while deliberately setting aside questions about its meaning. The equation worked, and that alone made it valuable. For experimentalists and applied scientists, predictive accuracy mattered more than philosophical interpretation. As long as the formula delivered correct results, its underlying assumptions could be treated as provisional or even ignored. Theoretical physicists, however, were less able to avoid the deeper implications. Quantization directly challenged the continuity that underpinned classical theory. For those who had spent their careers refining differential equations and continuous models, the idea of discrete energy exchanges felt like a retreat from rigor rather than an advance. Some regarded it as an admission of failure, a sign that physicists were resorting to artificial constraints instead of true explanations. Senior figures in the field were often the most resistant. Their authority had been built on classical frameworks that had proven extraordinarily successful. To accept quantization was to acknowledge that these frameworks were incomplete. This was not merely an intellectual concession, but a personal and professional one. As a result, many influential scientists urged caution, emphasizing the provisional nature of Planck's assumption. Others attempted to reinterpret quantization in ways that minimized its revolutionary character. They suggested that discreteness arose from the properties of matter rather than from energy itself. In this view, atoms might only be capable of exchanging energy in certain amounts, while radiation remained fundamentally continuous. This interpretation preserved the wave theory of light and allowed classical electromagnetism to survive largely intact. This compromise was appealing because it localized the disruption. Instead of requiring a complete overhaul of physics, it confined the problem to the poorly understood domain of atomic structure. Since atoms were already mysterious, attributing quantization to them seemed reasonable. For a time, this approach allowed physicists to use quantum ideas without fully committing to their broader implications. Yet even this limited acceptance generated unease. If atoms imposed discrete rules on energy exchange, then classical mechanics could no longer describe atomic behavior accurately. This realization raised new questions about stability, motion, and radiation at the microscopic scale. The attempt to isolate quantization ultimately spread its influence rather than containing it. Younger physicists tended to be more open to these ideas. Less invested in classical traditions, they were more willing to explore new approaches if they promised explanatory power. They saw quantization not as a threat, but as an opportunity to solve problems that had long resisted solution. This generational divide played a significant role in shaping the pace of acceptance. Scientific journals of the period reflected this diversity of opinion. Papers using Planck's constant appeared alongside works that ignored or criticized it. Conferences and seminars became arenas for debate, where supporters and skeptics confronted each other with arguments grounded in both theory and experiment. These discussions were often intense but generally respectful, reflecting a shared commitment to empirical truth. Experimental evidence gradually tipped the balance. As quantization proved useful in explaining phenomena beyond blackbody radiation, resistance weakened. Each successful application made it harder to dismiss the idea as an isolated fix. The consistency with which Planck's constant appeared across different contexts suggested that it was not an accident but a fundamental feature of nature. Nevertheless, acceptance was uneven. Some areas of physics incorporated quantum ideas rapidly, while others remained largely classical. This unevenness created a patchwork of theories that coexisted uneasily. Physicists navigated this landscape pragmatically, using whatever tools worked best for the problem at hand. The resistance to quantization also reflected broader philosophical concerns. Classical physics had provided a clear, intuitive picture of the world, one that aligned well with everyday experience. Quantization threatened this clarity, replacing it with abstract rules and counterintuitive concepts. For many scientists, this loss of visualization was deeply unsettling. There was also concern about the direction science was taking. If fundamental theories became too abstract, would they remain connected to physical reality? Would physics turn into a purely mathematical exercise, detached from observation and intuition? These questions were not trivial, and they influenced how new ideas were judged. Despite these concerns, the practical success of quantum ideas could not be ignored. Engineers and experimentalists found that calculations involving Planck's constant yielded accurate predictions. This practical utility helped normalize the concept, even among those who remained philosophically uneasy. Over time, the tone of discussion shifted. What had once been framed as a radical departure began to be seen as a necessary extension of existing theory. Quantization was no longer an intruder, but a tool that expanded the reach of physics. This shift did not eliminate resistance, but it softened it. The reactions within the scientific community illustrate how knowledge advances through negotiation rather than sudden consensus. New ideas are tested not only against data, but against existing beliefs, methods, and values. Acceptance is gradual, shaped by evidence, debate, and generational change. Planck himself observed these reactions with a mixture of pride and discomfort. He was pleased that his work was taken seriously, but he remained cautious about its interpretation. His own ambivalence mirrored the broader uncertainty of the field. As the years passed, the accumulation of evidence made continued resistance increasingly difficult to justify. Quantization proved indispensable for understanding radiation, atomic behavior, and energy exchange. The question shifted from whether the idea should be accepted to how its implications should be understood. This period of reaction and resistance was essential to the development of quantum physics. It forced proponents to refine their arguments, clarify their assumptions, and seek stronger experimental support. Skepticism, rather than hindering progress, helped shape a more robust theory. By engaging critically with quantization, the scientific community ensured that its eventual acceptance was grounded in evidence rather than enthusiasm. The debates of this era laid the intellectual groundwork for the more formal development of quantum theory that would soon follow. The resistance gradually gave way not to blind acceptance, but to a deeper recognition that classical physics had limits. Quantization did not destroy the classical framework. It revealed where and why it failed. This realization allowed physicists to move forward without abandoning the achievements of the past. The story of these reactions shows that revolutionary ideas in science often face their greatest challenge not from lack of evidence, but from the weight of established success. Quantization had to earn its place by proving itself repeatedly. In doing so, It transformed skepticism into a driving force for understanding, preparing the scientific community for the profound changes that lay ahead. In the years that followed the uneasy acceptance of quantization, the true significance of Planck's smallest action began to reveal itself in ways no one had initially anticipated. What started as a cautious mathematical assumption slowly emerged as a universal constant, woven into the fabric of physical reality. The constant that had first appeared as a technical parameter in an equation began to act like a boundary marker, quietly defining what nature would allow and what it would forbid. Physicists gradually realized that Planck's constant was not tied to a specific material, radiation source, or experimental setup. It appeared everywhere energy was exchanged at the microscopic scale. This universality was unsettling and profound. Constants in physics were not mere numbers. They represented deep properties of nature. If Planck's constant appeared consistently across unrelated phenomena, it suggested that discreteness was not an artifact of a particular system, but a fundamental feature of the universe itself. As new experiments accumulated, the constant revealed its role as a scale, setter. Whenever physical action became comparable in size to Planck's constant, classical predictions began to fail. Motions no longer followed smooth trajectories, energies no longer varied continuously, and probabilities replaced certainties. Conversely, when actions were enormous compared to this constant, classical physics re-emerged as an excellent approximation. This explained why everyday experience appeared continuous and deterministic, while the atomic world behaved so differently. This insight reframed the relationship between classical and quantum physics. Classical laws were not wrong, they were incomplete. They described a limiting case where Planck's constant was effectively negligible. The smallest action did not overthrow centuries of physics, but placed them within a broader framework. This reconciliation eased some philosophical resistance, showing that quantization did not deny classical success, but explained its boundaries. The constant also forced physicists to rethink the meaning of measurement. In classical physics, quantities like position and momentum could, in principle, be known with arbitrary precision. Planck's smallest action suggested otherwise. If nature itself imposed a minimum scale on physical processes, then attempts to measure below that scale would inevitably disturb the system. This realization planted the seeds for a new understanding of observation, one in which the act of measuring became inseparable from the phenomena being measured. As theory advanced, Planck's constant began to appear in unexpected places. It governed the stability of atoms, explaining why electrons did not spiral into nuclei. It shaped the spectra of light emitted by excited gases. It determined the thresholds at which electrons could be ejected from metals. Each appearance reinforced the sense that this constant was not an isolated curiosity, but a central organizing principle. The smallest action also reshaped how physicists thought about change itself. In the classical world, change was smooth and infinitely divisible. With quantization, change became granular. Systems transitioned between states in jumps rather than slides. This challenged intuition but aligned perfectly with experimental results. Nature, it seemed, preferred discrete steps over continuous motion at its deepest level. The philosophical implications were impossible to ignore. If the universe operated with built-in limits, then determinism had to be reconsidered. Outcomes could no longer be predicted with absolute certainty, only with probabilities. Planck himself had been uncomfortable with this implication, yet his constant made it unavoidable. The smallest action introduced an element of irreducible uncertainty into the laws of physics. This uncertainty was not due to ignorance or experimental imperfection. It arose from the structure of reality itself. Planck's constant set a fundamental limit on how precisely certain pairs of quantities could be known. This idea transformed ignorance from a practical limitation into a principle of nature. Knowledge itself now had boundaries. The emergence of this principle changed the goals of physics. Instead of seeking exact predictions for individual events, physicists began to focus on statistical patterns and expectation values. Laws described distributions rather than trajectories. This shift marked a profound change in scientific thinking, one that extended far beyond the original problem of blackbody radiation. The smallest action also unified diverse areas of physics. Phenomena that once seemed unrelated were now connected through a single constant. Thermal radiation, atomic spectra, chemical bonding, and electrical conduction all depended on the same fundamental scale. This unity hinted at a deeper coherence underlying the apparent complexity of the physical world. As the constant gained acceptance, it became a bridge between theory and experiment. Its numerical value could be measured with increasing precision, providing a benchmark for testing new ideas. Any theory that failed to reproduce Planck's constant in the appropriate limits was immediately suspect. In this way, the smallest action became a guiding constraint, shaping the development of future theories. The broader impact of this realization extended beyond physics. It influenced philosophy, technology, and even culture. Technologies such as semiconductors, lasers, and later quantum computing relied directly on principles governed by Planck's constant. What began as an abstract idea became the foundation of modern technological civilization. Yet despite its importance, the constant remained conceptually elusive. It resisted simple visualization. Unlike mass or charge, it did not correspond to a tangible substance. Instead, it encoded a relationship between energy, time, and change. Understanding it required abandoning familiar metaphors and embracing abstraction. This abstraction became a defining feature of modern physics. Equations took precedence over pictures. Mathematical consistency became as important as intuitive clarity. Planck's smallest action played a central role in this transition, signaling a new era in which the deepest truths of nature were revealed not through direct sensory analogy, but through mathematical structure. Looking back, it became clear that the discovery of the smallest action was not just the birth of quantum physics, but a turning point in human understanding. It revealed that the universe operates with limits, scales, and rules that defy everyday intuition. It showed that certainty has boundaries and that knowledge itself is constrained by the nature of reality. The significance of this realization continues to unfold. Even today, physicists explore how Planck's constant interacts with gravity and spacetime, probing regimes where current theories break down. The smallest action remains a beacon, guiding inquiry into the unknown. In this way, Planck's modest assumption evolved into a cornerstone of modern science. What began as a desperate attempt to fit experimental data became a profound statement about the structure of the universe. The smallest action turned out to be anything but small in its consequences, reshaping physics and redefining humanity's place within the cosmos.